Okay, this video is about motion graphs. Before we begin, what I'd like for you to do is answer me two questions. What does the slope of a position time graph tell you? And also, what does the slope of a velocity time graph tell you? Go ahead and pause the video and see if you can give me the answer. Okay, so for a position time graph, let's take a look here. We've got our slope here, and when we calculate our slope, it's our rise over our run. So if we take a look at just the units of my rise units over my run units, that can tell us something about it. It's meters per second. And so therefore the slope of our rise over run is meters per second, which is what we call velocity. So the slope of a position time graph is velocity. Let's take a look at the velocity time graph. So again, let's take a look at the units of my rise units over my run units. So the slope of my rise units over my run units is going to be in meters per second, which is also meters per second squared, but those are the units for acceleration. So the slope of a velocity time graph is acceleration. So today what we're going to do is predict the shapes of a velocity time graph and an acceleration time graphs if given the position time graphs. And we'll get that near the end there. But before we go to there, let's go ahead and analyze some graphs here. Okay, so these series of graphs that I have here are from a website that I highly recommend for learning physics. It's called thephysicsclassroom.com. And I'm going to tell you, it's one of the oldest websites that I know of that teaches physics. And it's a really good site, and it's still valid after all these years here. So I've got a file here, a GIF file, and it's showing the constant velocity here. And so notice that the positioning or the change in position as time goes on between these two little dots, all these spaces between these dots, they're all the same. They're equal distances from each other. So we have an equal spacing of dots, therefore we're going to have a constant change in position as time goes on. So if we take a look at our rise over run, as time goes on, the rise over run, the change in our position per change over time is going to be the same. No matter where we are on this line, the change in position will always be the same per unit of time. Okay, so let's take a look here. So if I were to calculate the slope here, remember the slope of a position time graph gives me velocity. So if I calculate the slope to be about 12 meters per second, therefore, my velocity graph is going to show a velocity of 12 meters per second. Even if it's a few seconds later, the slope is still the same. It's constant. So therefore, my velocity is going to be constant. Again, my slope is going to be 12 meters per second anywhere on this line. Therefore, my velocity is going to be 12 meters per second throughout the entire time here. So let's go from velocity to acceleration. So the velocity of the slope of a velocity time graph gives me acceleration. So if I calculate the slope of this velocity time graph, it comes out to be 0 meters per second squared, which is also the acceleration. 0 slope, 0 acceleration. No matter where we are in time, the slope is always going to be 0, so therefore my acceleration is going to be 0. Let's move on. Okay, now we're going to accelerate in the positive direction. Now notice as time goes on, the spacings get further and further apart. Okay, so here the spacings are close together, but as time goes on, you can see they're spacing out further and further. And what we'll notice here is, let's talk about our slopes here. We've got our slope or our rise over run here is this change in position as this time goes on. But if we move on to the next time frame, the spacing gets further out between the position. And then if I go to the third time frame, again, the spacing gets further out as well, just like the spaces here in our particle diagram gets further out as time goes on. Okay, so if we take a look at the slope at the very beginning, it's about a 0 there. And what I'm doing here is I'm drawing what's called a tangent line. And a tangent line is a line that just barely touches the graph at that point. So because the slope is 0, at that time frame, I've got a velocity of 0. If If I move further in time here, I've got a line of a tangent here that's just barely touching this graph here. And if you calculate the slope to be 8 meters per second, well, therefore your velocity is going to be 8 meters per second at the same time frame. Okay, at 5 seconds here, 5 seconds here. Moving forward, I've got a higher slope here of 17 meters per second. So here's my tangent line, and it's 17 meters per second is the slope. Therefore, my velocity is going to be 17 meters per second at that time. So as time goes on, the slope of our position time graph is constantly increasing. So time goes on, my slope gets higher and higher. And as my slope gets higher and higher, my velocity gets higher as well. Here I got a 0 slope, 0 velocity. 8 slope, 8 velocity. 17 slope, 17 velocity. Now, let's take a look at this one more time. So again, as time goes on, the spacing gets further and further apart. Therefore, my velocity gets higher and higher. Now let's go to velocity and acceleration. Well, the slope for a velocity time graph is acceleration, and the slope is constant. If I were to calculate the slope of 1.8 meters per second squared, that is going to give me my acceleration. Okay, so let's accelerate in the positive direction. But wait a minute. So accelerating in the positive direction, this thing is slowing down. That's true. Because remember, acceleration is the change in velocity. It doesn't mean that we're slowing down or speeding up. All it really means is that we're changing the velocity. So you can accelerate in the positive direction. It's not that you're decelerating or slowing down. It's the change in velocity that tells you what's going on here. So remember, acceleration is the change in velocity over time. So as we see here, the spaces between the positions get shorter and shorter. And we'll notice here that the object is going to be slowing down here. So let's take a look at it. All right, so we've got a really, really high tangent line at the very beginning. And then it gets a little lower, and then a little lower, and then a little lower. So as time goes on, the slope of our position time graph, that tangent line, is constantly decreasing. And so therefore we have a constant negative velocity there. Okay? And now we have a negative slope. Because we have a negative slope in our velocity time graph and it's constant, the negative slope is going to give me a negative acceleration value there. Let's speed up in the negative direction. I'm not going to go through through all the other graphs for you like I did earlier, but we can analyze this real quickly. Notice here at the very beginning, I've got a 0 slope as my tangent, so I should have a 0 velocity. As I move forward in time, I've got a negative slope here, but as time goes on, the tangent line gets more and more negative, so therefore my velocity gets more and more negative as time goes on. I've got a negative slope here in my velocity time graph, and that's going to give me a negative acceleration. So let's slow down in the negative direction. Okay, so I've got my spacings, and as time goes on, those spacings get closer and closer together. At the very beginning, I've got a really high negative slope, so I should have a high negative velocity. As time goes on, the slope gets progressively small until I get to the end here where I have a 0 slope. So at this point here, at 15 seconds, I should have a 0 velocity. And I have a constant positive velocity here, so therefore I'm going to have a constant positive acceleration. So now let's see if we can tackle this problem here. We've got some position time graphs, and for each of these position time graphs, let's see if we can predict the velocity time graphs and acceleration time graphs. Let's start with the first one here. Okay, if I draw my tangent line, it's going to be a really high positive tangent line. So therefore, I should have a positive velocity at that time or during that time frame. Notice here at the very top of this little curve here, I've got a 0 slope. So you should be able to predict, because the slope is 0, we should have a 0 velocity at that time frame, and we do. Now, if we were to draw a tangent line over here, it would be a negative tangent line, so therefore, or a negative slope, so therefore we can conclude that we have a negative velocity over here. See, my positive velocity is over here, my negative velocity is over here. I should have put a 0 here, but I didn't. But if I were to put a negative here, this would be my negative velocity. Let's try the second one here. Now over here, maybe you can kind of predict here, but you've got a positive slope here. It looks like we have a really high positive tangent line at the very beginning. Therefore, I'm going to have my positive velocity in this area. And then here, in the middle of this graph, I've got a 0 slope here. So I should have a 0 velocity at that point. And then here, it looks like I can have a positive slope here. So therefore, I'm going to have a positive velocity going here. Now this third and last one, if I were to draw a line here, well, the tangent line to this one is going to be pretty easy. It's going to be a 0 slope, so therefore I'm going to have a 0 velocity. But then as time goes on, I'll have a little positive slope here, therefore I'm going to have a positive velocity. Now, moving on. So I've got a negative velocity here. It's constant. It's the same throughout. So if we take a look, from here we've got a positive velocity, but it's a negative slope. Because we've got a negative slope, we're going to have a negative acceleration. Moving on, well, we still have a negative slope, but as we continue on, we still have a negative slope. So therefore, I'm going to have a straight line going straight across for my acceleration. Now, taking a look here, I've got a negative slope, and then I've got a positive slope. So if we start at the beginning, the negative slope tells me I have a negative acceleration. I still have a negative slope even here, but then when I switch from here over to the next part, then I have a positive slope, and that positive slope is going to give me a positive direction or acceleration. And it's okay to cut the graph and move it up here. This is not a function. We're not dealing with functions. This is not math. This is an application of math. From here, we can say that there's a jump from here to here, or a step function, or whatever you want to call that. Moving on, we still have a positive slope, so therefore we're going to have a positive acceleration. Constant negative, constant acceleration. Constant positive, constant acceleration. Now the last one here, I have 0 slope. So because of 0 slope, I should have a 0 acceleration. Then I jump from a 0 to a positive slope here. So therefore I should have a positive acceleration. All right, well, thanks for watching. And remember, if you need help in tutoring in Phoenix, just give me an email at monroe.watson@gmail.com. Or if you have any questions or issues, just let me know.